Hey everybody, today we're going to get into the second fundamental theorem of calculus. As we think ahead to Calculus 2, this is probably the single most useful and important theorem just from a practical standpoint of being able to solve problems. Let's get into it. So remember, the first fundamental theorem of calculus said that if we differentiate an integral, we can get the original function back. In a very specific sense, right? We have an integral that is an accumulation function, where the variable that we're interested in is in the upper limit of integration. The second fundamental theorem of calculus says that if you integrate a derivative, you get the original function back. But again, in a very specific sense. So here, big F is an antiderivative of little f, and to evaluate the definite integral of little f, we're taking that antiderivative and then plugging in the limits of integration. We're doing big F of b minus big F of a and then subtracting. This becomes intuitive very quickly as we work through some examples. So let's do that. Let's look at the integral from 1 to 3, x squared plus 4x minus 5. We're going to evaluate this just by finding an antiderivative of x squared plus 4x minus 5, and then plugging in two values. So here's an antiderivative. That notation with the vertical bar is just saying that we need to plug in 3, then we need to plug in 1, and then we need to subtract, like this. We've plugged in 3, we've plugged in 1. Those are the quantities in the big parentheses. Let's simplify this a little bit. We end up getting 44/3. So notice that I didn't put in a plus c for the most general antiderivative. I left that out because I don't care about the most general antiderivative here. I just care about an antiderivative. Any one will work. Also, let's not lose sight of what this integral means. The integral from 1 to 3, x squared plus 4x minus 5 dx, is an area under a graph. From 1 to 3, the graph of this parabola. What we're saying is that that shaded area that I've shown here is actually 44/3. Let's do another one. Integral from 1 to 9, 2x squared minus 4 over the square root of x dx. We want to get an antiderivative here, but we need to do a little work first. There's no quotient rule for antidifferentiation. So we're going to simplify this. We're going to break up that quantity 2x squared minus 4 over the square root of x into two pieces. 2x squared over the square root of x and negative 4 over the square root of x. And then I'll simplify the exponents. 2x squared over the square root of x is 2x to the 3/2. Similarly, negative 4 over the square root of x is negative 4x to the negative 1/2. And now I can antidifferentiate directly. Raise up the power, multiply by the reciprocal in each of those two cases. I've left out the vertical bar. I've just put the limits of integration on that big parenthesis. So hopefully that notation is clear. It certainly gets intuitive very quickly as you do a few examples for yourself. So we plug in 9, and we plug in 1, and we subtract. We do a little arithmetic, remembering that a 1/2 power is a square root. And we end up getting 177 3/5. One more example. Integral from negative 1 to 3, 5 plus x to the 3rd. So here we need an antiderivative of 5 plus x to the 3rd. We know that when we differentiate, powers go down. When we antidifferentiate, powers go up. So we're going to get something like 5 plus x to the 4th. Now, when I differentiate 5 plus x to the 4th, I'll get a factor of 4 in front that I don't want. So I'm going to include a 1/4 here. Now when I differentiate 1/4, 5 plus x to the 4th, I get the thing that I have in the integrand there on the left, 5 plus x to the 3rd. I need to evaluate that from negative 1 to 3. Let's plug in 3. Let's plug in negative 1. And then simplify a little bit. We get 960. So the integral from negative 1 to 3, 5 plus x to the 3rd dx is 960.